Astronomy. Everyone knows that astronomers study stars and planets by using telescopes to capture as much of their light as possible. Many amazing photographs have been made by several cameras attached to these telescopes. The cameras on the Hubble and James Webb telescopes in space, in particular, have produced images that have fascinated people, millions of people worldwide. The spectacular images that adorn the walls of this room were made by members of this club. What you may not appreciate is the work done by another instrument, the spectrograph. Spectrographs use various means to separate incoming light into its constituent colors. One of these means is the glass spectrum, which Isaac Newton used in the 17th century to prove that white light is composed of a spectrum of colors, each distinguished by how much it's bent or refracted when entering or exiting a prism. Modern astronomical spectrographs, however, mostly use something called a diffraction grating of various types that separate colors into starlight far more accurately than glass prisms can. First, we'll discuss the electromagnetic spectrum, specifically how some wavelengths are absorbed by the atmosphere of the Earth. Second, I'll explain what astronomers can learn about the universe from spectra. Third, I'll show you how astronomers obtain spectra from starlight. And fourth, I'll describe 4 important spectrographs and some research done with them. So, a huge amount of radiation hits the Earth all the time, every second. And that radiation contains lots of information. And the radiation includes particles like cosmic rays, the solar wind, neutrinos. There are also gravitational waves and the full range of electromagnetic radiation, which you see on this diagram, from long wavelength radio waves on the right up to short wavelength high energy gamma rays. Unfortunately for astronomers, the Earth's atmosphere blocks 100% of the radiation at most wavelengths. Although the Earth's atmosphere is largely transparent to visible light, it's opaque to most ultraviolet light, only somewhat transparent to some wavelengths of near and mid-infrared light, opaque to far infrared light, and transparent to microwave radiation, and then totally opaque to longer radio waves. Optical telescopes such as those at Paranal Observatory in Chile and Kitt Peak National Observatory in Arizona mostly utilize visible light and near-infrared light to those wavelengths to which the atmosphere is mostly transparent. Because infrared light's absorbed by moisture, the dryness of places like Chile's Atacama Desert is important. But even there, it's important to locate telescopes in high altitude to further minimize the water in the atmosphere between a telescope and the stars. Another reason to build observatories at high altitude is to minimize the effects of atmospheric turbulence. Paranal, for example, is over 8,600 feet above sea level. Radio telescopes such as those elsewhere in the Atacama operate at millimeter and submillimeter wavelengths. And water in the atmosphere also absorbs radiation at these wavelengths, so it's important also for radio telescopes to be located at very high altitudes, such as the 16,400-foot Chachnantor Plateau in Chile, home to ALMA, the ALMA large millimeter array of radio telescopes. Space-based telescopes, of course, have a great advantage over Earth-based scopes, but they're far more expensive. For observing in some wavelengths, such as gamma rays, X-rays, ultraviolet radiation, and much infrared light, space telescopes are essential. But it's amazing how much can still be learned from Earth-based telescopes. We learn in high school science that white light is composed of many colors, from red to violet, which can be separated by a spectrograph using a prism or a diffraction grating. When we point a telescope with a spectrograph at an idealized, very hot object, the spectrograph would record a continuous spectrum of colors. However, if there's a cloud of gas between the star and a spectrograph, the atoms of the gas will absorb some of the light, causing dark absorption lines in the star's spectrum that can be analyzed to determine what elements are present in the cloud. Similarly, if a telescope is pointed at a portion of the cloud illuminated from the side by a star, the spectrograph will record just bright emission lines, whose color depends once again on which elements are present in the gas to absorb and re-emit those specific colors. Much of what we know about the composition, structure, and behavior of planets, stars, and galaxies has been derived from emission and absorption lines in spectra. It turns out that each element, like oxygen, carbon, hydrogen, etc., each element has a unique signature, its absorption or emission lines. And they signify the presence of that material in the sample you're looking at. So this graphic shows the visible light spectroscopy signatures of 4 common elements. Both the emission and the absorption lines correspond to the transitions between different energy levels of an atom, the energy levels in the electron cloud of an atom. Astronomers use spectrographs to determine what elements are present in stars and planetary atmosphere, as well as in clouds of gas between emitters of light and us. Astronomers also use spectrographs to determine how fast a star or a whole galaxy is moving towards or away from us. Subtle shifts in a star's spectrum can indicate the presence of exoplanets. Note the orange sodium emission line. That's the same color produced by sodium vapor streetlights and by the lasers in the adaptive optics systems at, for example, Paranal Observatory. And it depends, by the way, in the adaptive optics on the presence of a sodium layer high up in the Earth's atmosphere to create artificial stars. But that's a topic for another lecture. The principal classification of stars is based on their spectra. This graphic shows the visible light spectra of 7 types of stars, from hot O and B stars like Alnitak and Rigel in the constellation Orion, to the cooler K and M stars like Arcturus in Boötes and Betelgeuse in Orion. The farther the black absorption lines are from their normal positions, the faster a star is moving towards or away from us. Notice that O stars contain only hydrogen and helium in their outer layers. Notice also the presence of many molecules in the outer layers of M-type stars. Helium was discovered spectrographically in the sun before it was discovered on Earth. The sizes given in the table, by the way, are for typical members of each spectral class. Obviously, the red supergiant Betelgeuse is not just 70% the size of the sun. Okay, now we're going to talk about one of the two methods of discovering exoplanets. The one we're not going to talk about is called the transit method, which requires a planet to pass in front of a star and thus dim its light a little bit. This other method works even when the planet is not between us and the star. And so I'm talking about it because it uses the star's spectrum to determine the presence of the exoplanet or planets. It's called the radial velocity method, detecting exoplanet. And it looks for periodic shifts in a star's spectrum. If a planet orbits a star and the star and the planet are both in orbit about the system's center of gravity, it's like a giant and a dwarf holding hands and sort of dancing around a spot on the floor. The giant's probably just going to pivot around close to the point, and the dwarf's going to move around like that. So that's the idea. And in stellar terms, the star just appears to wobble a little bit, and that makes its spectrum change. So when the planet goes behind the star, the red arrow, the star wobbles away from the Earth. There's a dwarf's going that way and the giant's going this way. Okay, so the star wobbles toward the Earth and its spectrum, including any absorption lines, shifts toward the blue. When the planet moves in front of the star, the blue arrow, the star wobbles away from the Earth and its spectrum, including any absorption lines, shifts toward the red. Yes, the colors of the red and blue arrows should be reversed. This I won't credit who you can read yourself who created it. So these shifts are very slight and require a very high resolution spectrograph to detect them. One of these is ESPRESSO at Paternal Observatory, which I'll tell you about later. So light is separated into a spectrum of its constituent colors by a process called dispersion. There are three basic types of dispersers: prisms, reflective gratings, including the high resolution Echelle gratings, and the third type is transmission gratings, including the volume phase holographic gratings, which we'll talk about Echelle and VPH gratings later. So, as Isaac Newton discovered, white light can be dispersed by a glass prism into a spectrum of colors, with red being bent the least and violet the most. Prisms have several important properties. First, the shorter its wavelength, the more a color is bent by a prism, excuse me. Second, prisms are transparent, so they have very high throughput of light. Third, prisms are transparent to a wide range of wavelengths. And fourth, prisms are small enough to be part of a spectrograph, have low dispersion. They don't separate colors very well, so spectral lines can blur together, making it harder to determine the presence of elements. Now, dispersion is measured by its R value. This is going to come up again, so I want to define the R value for you. It's a function of wavelength, and it's the wavelength divided by the difference in wavelengths of the smallest spectral lines that can be separated by the disperser, or prism in this case, near the wavelength. So in case, so it's just lambda divided by delta lambda. For example, near the red wavelength of 700 nanometers, suppose the closest spectral lines that a prism can separate are 7 nanometers apart. Then the R value of the prism at 700 nanometers is 700 divided by 7, or 100. Prisms typically have R values between 30 and 300. Now, the most common technology used in astronomical spectrographs is the diffraction grating. Diffraction gratings can either reflect or transmit dispersed light. The shell gratings, like the one in the photo, reflect dispersed light. This particular shell grating is now installed in the ESPRESSO spectrograph at the Very Large Telescope at Paranal Observatory in Chile. A reflective grating has thousands of reflective elements. They're arranged in parallel grooves or etchings or patterns on the surface of the grating. As the wavelengths from these tiny surfaces interfere with each other it's a process called diffraction, a reflective grating produces multiple spectra called orders. Compare Well, the lower orders are brighter, but higher orders give better separation of colors, which is why we're interested in gratings in the first place. So compare the lower order -1 with the higher order -4, and you can see that we're already getting better dispersion, but lower brightness. For this reason, higher order spectra are used in astronomical spectrographs, even orders as high as 50 or 100. The colors resulting from a wide beam of white light can overlap. You can see that orders -3 and -4, and also -4 and -5, are beginning to overlap. So dispersion perpendicular to the slide is also needed to separate multiple spectral orders. So if two orders are being sent in the same two wavelengths of light, red and violet, for example, are being sent together by two different etchings in that grating, they're going to end up on the prism, and the prism is going to split them apart. So that second dispersion is performed by what's called a cross disperser. And you'll see some examples of those as we go forward. Okay, the higher order spectra produced by the shell diffraction gratings offer, as I said, very high resolution of spectral lines. The R value of a shell gratings range from 20,000 to almost 200,000. However, the higher order spectra, as I mentioned, are also dimmer, causing lower throughput of light. The spectral orders produced by shell gratings are also overlap, which, as I mentioned, also require cross dispersers to spread out the orders in a particular direction. In this example, light enters a spectrograph through a slit, and the shell grating disperses the light into a series of overlapping spectral orders. Then a cross-dispersing prism separates the spectral orders before the camera focuses the spectral orders onto a CCD detector. Some astronomical spectrographs use transmission gratings instead of reflective gratings. Here is a photo of a volume phase holographic grating used in DESI, the dark energy spectrograph instrument we'll talk about later. The VPHGs provide much more dispersion of colors than prisms do, but usually lower spectral resolution than the shell gratings. Instruments that use the VPH gratings typically have lower spectral resolution requirements, such as multi-object survey spectrographs like MUSE and DESI, which I'll tell you about later. Typical R values are 1,000 to 5,000, but can range up to 20,000 for the volume phase holographic gratings. And it turns out that these VPH gratings disperse most of the light's energy into a single spectral order, so its efficiency is high. Okay, now we're going to talk about how you can select which objects in a field of stars or planets, whatever, you want to take spectra of. So now that we know what spectra are good for and have some means of producing spectra, prisms or gratings, how do we select the objects? Well, given that a star field is two-dimensional and that a spectrum of a point source is one-dimensional, it's a challenge to produce a spectrum for each object in that star field without causing the spectra to overlap. One solution is to place a long slit between the star field and the spectrograph, effectively reducing the star field to one dimension. Another solution is to split the star field optically into multiple segments that can be processed independently, routed in different directions. A third solution is to sample the star field with one up to thousands of optical fibers that route light in bundles into a set of spectrographs. Imagine we pointed our telescope to a star field and want the spectrum of each star. As I said, one approach would be to feed the entire field into a spectrograph, and then you'd be cramming a third dimension wavelength, that is color, into a two-dimensional image, as in this lower picture on your left. Okay, and that would create a smear of spectra such that the brightest objects would dominate. A simple solution to the problem is to use what I mentioned on the previous slide, a long slit spectrograph, in which only a sliver of the entire field is fed into the spectrograph at one time. Of course, we would have to make many spectrograms, one for each position of the slit in the star field. It turns out that two long slit spectroscopy is one of the modes of NIRSpec, the spectrograph on the James Webb that I'll talk about later. Now this slide's a bit complicated, but it has great power, I think, to help your intuition understand about how spectroscopy is dealt with in modern astronomy. The basic problem is that there are 100 billion stars in the Milky Way, our galaxy. And from 100 billion to maybe 2 trillion galaxies. So observing the one or a few at a time with a long slit spectrograph is impractical. And so a type of instrument called an integral field spectrograph allows astronomers to record the spectrum of each tiny area of a region of the sky. MUSE at Potendal and NIRSpec aboard James Webb contain integral field spectrographs. Well, rather than getting a two-dimensional image of a part of the sky, an integral field spectrograph produces a three-dimensional data cube. Each two-dimensional pixel has a spectrum. One type of IFS uses a slice and dice approach. The field of view from a telescope is divided optically, not digitally. No information is lost here. It's divided optically into slices called mini slits. Each slit is injected into a spectrograph, and the spectrograph disperses the light into onto a CCD detector. So let's see now. The detector counts the photons falling on each pixel. Now the result is a data cube, as I mentioned, and that's, you can see 3 slices through the data cube there, blue, green, and red. Each spatial layer corresponds to a Each spatial layer corresponds to a particular color or wavelength. The number at each spatial point measures the intensity of the color at that point. the arrow is pointing to an image generated from the data cube. But you also want to get numerical values, basically the counts of photons hitting the detectors. And for that, you need to look at what I call a data line, which is that line there between, it's a line through the same pixel on the sky, but the CCD at that point counts blue photons, the one at the middle point counts green photons, and the one at the red point, red photons. So what we're going to do is now talk about a different means of selection. We've talked about long slit, we've talked about integral field spectroscopy. Now we're going to talk about fiber optic sampling. ESPRESSO at Polygonal and DESI on Kitt Peak use fiber optic sampling to select objects for study. In fiber optic sampling, one or more optical fibers are positioned to receive the focused light from particular objects in the field of view. The optical fibers are bundled into a cable that then goes to a pseudo-slit termination in a spectrograph. Okay, so now that we've got the basics of how to produce spectra, how to select objects, we're going to go on to looking at individual spectrographs around the world. The first one is MUSE, the multi-unit spectroscopic explorer installed in 2014 at Polygonal Observatory in Chile. The next one is ESPRESSO, the shell spectrograph for rocky exoplanets and stable spectroscopic observations, installed in 2017, also at Polygonal. Third, we'll talk about DESI. DESI, I just learned, is pronounced DESI. And it reminds me of 2001, A Space Odyssey, where the computer HAL gradually loses its mind and at the end is singing Daisy, Daisy. Anyway, on to the lecture. DESI is the dark energy spectroscopic instrument installed in 2019 at Kitt Peak National Observatory in Arizona. And the final one we'll talk about is NIRSpec, the near-infrared spectrograph, which reached orbit on the James Webb Space Telescope in 2021. So, MUSE. MUSE was installed in 2014, as I mentioned, on the 8.2 meter unit telescope number 4, named Yepuan, at Polygonal Observatory in Chile's Atacama Desert, the driest place on Earth. Polygonal is operated by the European Southern Observatory, or ESO. MUSE produces spectra in the visible light and near-infrared light wavelengths. The field of view of MUSE is divided optically into 24 channels, and each of those channels is fed to its own integral field spectrograph. So this is another, there are two layers of optical division in this case. We've only talked about the second level, but MUSE adds a first level to get even more information in one image. So, so MUSE's field of view is divided into 24 image channels, and each channel has 24 integral field units, they're called in the literature there, one per channel, arranged in 4 rows of 6. I'll show you a photo that I took of that later. Each IFU further divides its channel optically into 48 slices called mini slits. And those mini slits are what are then injected into the IFU spectrograph, which disperses the light using a volume phase holographic grating. And it's only that dispersed light after 2 levels of optical slicing that actually hits the CCT detectors and the information is digitized. So MUSE records 400 million pixels, where each pixel has a full spectrum with R value ranging from 1800 to 3600. And I should mention that MUSE has wide and narrow fields of view. The wide field has a 1 arc minute width, and the narrow field 7.5 arc seconds. There's 60 arc minutes in a degree. The full moon is half a degree wide. Okay. Now, what sort of research does MUSE perform? Why are spectrographic instruments so important? What do we get? Well, astronomers use MUSE to conduct research on the evolution of galaxies over cosmic time. Remember, the further out you can look, the further back in time you're looking, up to billions, 10 billion light years or more. So that's how we can study evolution through astronomy. MUSE is also used to study the structure and motion of nearby galaxies, study individual stars and stellar populations like dense clusters and star-forming regions. It's used to study objects in the solar system, to see about what elements are in the volcanoes erupting from the surface of Jupiter's moon, Io. And finally, we depend on serendipity, of targets of opportunity popping up, and I'll tell you of one of those later. So this is the photograph I mentioned. I took it when Nancy, my wife, there in July of 2023, visited Patternal Observatory. Here you see the back ends of the 24 integral field spectrographs, which are arranged in 4 rows of 6. ESO, European Southern Observatory, likes to point out that the James Bond movie Quantum of Solace was filmed at Patternal's residence hall. But don't you think that MUSE looks like it could have been used in filming The Matrix? This example shows how MUSE slices and dices its wide field mode images. Again, this is a complicated slide, but it's well worth studying because you really get a sense of the difference between optical slicing and digitization, because it's a digitization that you can lose information due to the fact you have a finite number of pixels in a detector. Okay, so this example shows how MUSE slices and dices its wide field mode images. The first step is to optically split its field of view into 24 subfields, those channels I mentioned. Each channel is handled by one of 24 integral field units, or spectrographs. Each channel corresponds to the entire image in the earlier integral field spectroscopy slide, the data cube slide that I showed. Each IFU optically splits its channel into 48 slices or mini slits. And each IFU has a spectrograph to which it presents all 48 slices simultaneously. But let's look at what happens to one such slice. The spectrograph uses a volume phase holographic grating to disperse the light of that slice onto a detector in a column of colors about 75 pixels wide and about 4,000 pixels long. Okay, so that's it's at that point that you have a digital record of the different spectral information in the image. So MUSE was used to discover the source of gravitational waves. This is one of the targets of opportunity, or an example of serendipity. MUSE was used to discover the source of gravitational waves detected by the ground-based LIGO and Virgo gravitational wave detectors, and gamma rays detected by the Fermi and Integral space-based telescopes. Spectroscopic evidence from MUSE proved that the source was a kilonova, the brilliant merging of two neutron stars. Well, so what? What's so important about merging neutron stars? This is another image that's worth some pondering. Merging neutron stars create 50 of the 92 elements found naturally in the solar system, including gold and uranium. In fact, it's the only source of uranium that we know about. Major subjects of astrophysics research are to understand the ways in which each element can be created in the process of stellar revolution, and to determine how the elements find their way into the clouds in which stars form and into the circumstellar disks in which planets form. And that's why studying the stellar nurseries that we call the Orion and Carina nebulas is so important. There, exploding massive stars contribute such elements that are important for life as carbon and oxygen. And there are other sources. Of course, hydrogen and helium come exclusively from the Big Bang. Excuse me, helium actually can be produced by stars through fusing hydrogen. So let me back off on that. Hydrogen certainly from the Big Bang. Also, you have dying low mass stars and exploding white dwarfs, cosmic ray fission as other sources. So this you can find this graphic on the web if you care to look at it in more detail. So the next spectrograph I'll tell you about is ESPRESSO, the planet finder. The Echelle spectrograph for rocky planets and stable spectrographic observations. Now you heard it twice. You think you could repeat it? Anyway, ESPRESSO, as I mentioned, was installed in 2017 at Paranal in its combined Coude lab, sort of underground at the peak of Paranal, the hill called Paranal. It's a very stable, high-resolution spectrograph. Its Echelle grating provides a spectral resolution between 70,000 and 190,000, which is essential for detecting the very slight shifting in a star's spectral lines caused by the presence of an exoplanet the same size as Earth. ESPRESSO functions with either one of the 4 8-meter unit telescopes or all 4 of them, depending on the resolution and light gathering power required. The first one is medium resolution, which gives a 1 arcsecond field and uses all 4 unit telescopes for maximum light gathering power. The high resolution also provides a 1 arcsecond field, but uses only 1 UT. And finally, ultra high resolution provides a 0.5 arcsecond field and uses 1 unit telescope. Well, ESPRESSO has 3 purposes, actually. The first purpose is to find and study Earth-like planets in the habitable zones of sun-like stars. But another purpose is to measure potential variations in what are currently thought to be physical constants of the universe, such as the ratio of the masses of the proton and the electron. A third purpose is to study the chemical composition of individual stars in nearby galaxies. This is a very busy diagram, so I'll go over it slowly. The four 8.2-meter unit telescopes at Paranal Observatory can operate together to form the Very Large Telescope for high precision interferometry, or for ESPRESSO, as the equivalent of a 16-meter telescope. The light from the four unit telescopes, and I'll show you the diagram for UT1, is routed by prisms and mirrors through long tunnels to the combined Cuday lab underneath the observatory platform where ESPRESSO is located. And ESPRESSO can combine the light from all four unit telescopes that come in that way, or simply use the light from one of them. The gray section in the top center is ESPRESSO's front end for receiving light from UT1. The front ends of UT2, UT3, UT4 have the same design. A couple of the front ends are pictured in the top right of the slide. The front ends condition the light and send it on to a fiber optic multiplexer that combines the light from all four unit telescopes. This is how four telescopes become one. The name of the four together is the Very Large Telescope. And people talk about the VLT like it was just one instrument sometimes. Anyway, the combined light is then fed into a single fiber into the spectrograph, which is inside a vacuum vessel. The vacuum vessel with protruding red and blue cameras is shown in the lower right corner. And there's another picture of the vacuum vessel in cross-section. And a shell grating to disperse the light, and various other optical elements to condition and direct the light are also present. ESPRESSO uses a shell grating spectral orders ranging from 80 to 170, with up to 90 recorded on the detectors simultaneously. And so let's look at the light path here. Light from ESPRESSO's front end enters the spectrograph through a single fiber. So the spectrum of only a single object will be produced at the shell grating, which is there. And the grating disperses the entering light into a series of spectral orders. The dichroic beam splitter then separates the shorter and longer wavelength portions of the orders. So that one range of colors go to the blue camera and one to the red camera. And the cross dispersers are there so that the overlapping orders of the spectra get separated before they're run into through the camera and into the detectors. Each stripe in the detector corresponds to one Eshell order. Within each stripe, wavelengths vary continuously, and adjacent stripes correspond to adjacent order numbers. That's how the astronomers can figure out what they've got after all this information is presented to them. And this is what the spectrum looks like on the system monitor when ESPRESSO was first given starlight. The data captured on the two CCD detector arrays were combined for display on the monitor. And here are some of the results obtained by using ESPRESSO. First, January 2021, 6 planets around TOI 178 in the Sculptor constellation, 200 light years away, were found by multiple instruments, including ESPRESSO. Interestingly enough, the Oops, ignore that. The 5 outer planets around TOI 178 orbit in resonance, while the second closest planet goes around the star 18 times, the third planet goes around 9 times, the fourth planet 6 times, and the other planet, fourth and fifth, 4 times and 3 times. So these are all synchronized, unlike in our solar system. So this second line there talks about the August 2021 announcement that the planetary system L9859, 35 light years from the sun, may have 5 planets, one of which may be in the habitable zone and have water. You've heard of the Goldilocks zone. That's it's the temperature and the presence of water are crucial for life as we know it. Third, we have February 2022, Proxima Centauri D was discovered in orbit about the star Proxima Centauri, which is closest to the sun. And Proxima Centauri D is the smallest exoplanet found to that date. In October 2022, the element barium, which is number 5, I think, on the periodic chart, was discovered in the atmospheres of the exoplanets WASP 76b and WASP 121b. In October 2024, at 35 light years from Earth, the Barnard star, its planet number letter B, became the closest exoplanet discovered around a single star. And then in February 2025, get this, their winds of the elements iron and titanium were discovered around WASP 121b. So a tremendous amount of information can be discovered when you have high resolution spectrographs like ESPRESSO. Okay, third, and for those in the audience here, you may have noticed my sweatshirt, which is from DESI. I found it in my wardrobe today. Anyway, so I wore it. So let's talk about DESI, the Dark Energy Spectrographing Instrument. The big black tube at the front end of DESI the big black tube is the front end of DESI in position on the 4-meter Mayall telescope on Kitt Peak. The tube contains corrective optics that support DESI's 3-degree field of view. Normally, a 4-meter astronomical telescope would have a tiny field of view, maybe an arc minute or two. But by using corrective optics, you can get rid of the distortions that prevent light from the mirror being used to see more in the sky. Anyway, those corrective optics support a 3-degree field of view. The tube also contains the terminations of 5,000 fiber optic cables that conduct light from the focal plane of DESI to 10 spectrographs nearby. Let's look at some of the properties of DESI. It's, as I said, the dark energy spectroscopic instrument installed on the 4-meter Mayall telescope on Kitt Peak in 2019. DESI has that extremely wide field of view that I mentioned, 3 degrees, and the 5,000 fiber optics samplers with their computer-controlled positioners. DESI is sensitive to wavelengths from 360 to 980 nanometers, which is basically violet to near infrared. And DESI's spectral resolution ranges from R equals 2,000 for violet to R equals 5,000 for near infrared. What kind of research does DESI is conducted with DESI? Well, you may have heard last month that a 5-year dark energy survey had completed the observations leading to a three-dimensional map of 47 billion galaxies. These observations were done using DESI. So astronomers have used DESI to map the large-scale structure of the universe. Because DESI is a spectrograph, you can tell from the redshift how far away the galaxy you're looking at is. And we'll talk more about redshift in a bit, but redshift is really key to getting more than a two-dimensional view of the heavens. You need to know how far things are, and therefore how far back in time. And it turns out there's a lot of structure in the universe that's only fairly recently been realized. Okay, so astronomers also hope to understand the expansion history of the universe. We're trying to understand, for example, what dark energy is. Is dark energy constant, or is it accelerating now, the expansion of the universe? DESI may also help to answer other questions. What are the rest masses of various kinds of neutrinos? Or is there a better theory than general relativity for explaining astronomical observations? Okay, light gets from the DESI focal plane to the 10 spectrographs through 5,000 optical cables installed in 10 500 fiber petals. This is one of the 10 petals. The fibers are positioned in their tiny domains by computer-controlled robots to an accuracy of 10 microns, less than the width of a human hair. Positioning the fibers takes only 2 minutes per observation. Here are the 10 three-arm spectrographs of DESI. Multi-object spectroscopy is a complicated business. Let's look next at the design of one of these spectrographs. The light entering each of the 10 DESI spectrographs is processed by 3 channels: near-infrared, red, and blue. Here are the details. 500 fibers from DESI's front end terminate in a slit in the infrared beam splitter. Light enters the spectrograph and hits the collimating mirror. From the perspective of the collimating mirror, the light looks like 500 points in a column. The collimating mirror reflects the light from the fibers into parallel beams that hit the infrared beam splitter. The infrared light passes through the beam splitter, but the visible light is reflected. The infrared light enters the IR channel and passes through a volume phase holographic grating that disperses the light. Something's gotten out of whack here. Oh well, I'll just have to talk you through it. Okay, well maybe it did right. I think it may have done right. Okay. And anyway, once it gets through, once it's dispersed, then it's focused onto the CCD detector for the infrared channel. Meanwhile, the visible light reflected from the IR beam hits the red beam splitter. The longer wavelength passes through the beam splitter, but the shorter wavelength light is reflected. The longer wavelength light enters the red channel, where a second holographic grating disperses it into a spectrum that's focused on the CCD of the red channel. The shorter wavelength light then enters the blue channel, simultaneously enters the blue channel, where a third grating disperses it into a spectrum that is then focused onto the CCD of the blue channel. So that's basically as the most complex optical path discussion you'll see tonight. So now for some results from the 5-year DESI project. The top part of this slide shows the triangulum galaxy, M33, superimposed on a representation of the 5,000 fiber optic terminations in the focal plane of DESI. The bottom part of the slide shows the resulting intensities in visible light and in infrared light as measured by the spectrograph for one of the fibers picking up light from M33. Each spectrograph splits the light from its 500 fibers into the 3 integral field units covering the blue end of the visible light spectrum, the red end, and the near-infrared spectrum. But the main output that this has yielded is a three-dimensional map of the universe of 47 billion galaxies in the universe. 35 were planned, but they actually did 47. And by studying the redshift of these galaxy spectra, stars were able to determine how the rate of expansion of the universe has changed, or will be able to determine how the rate of expansion of the universe has changed over 11 billion years of cosmic history. DESI has now measured cosmological data for 6 times as many galaxies and quasars as all previous measurements combined. The collaboration will immediately begin processing the completed data set with the first dark energy results from DESI's 5-year survey expected next year. And finally, NIRSpec, which was launched, as I mentioned, in 2021 aboard the James Webb. This shows the NIRSpec while it was still at its manufacturer. NIRSpec is the near-infrared spectrograph aboard the James Webb Space Telescope. It's in orbit around Earth's L2 Lagrange point. L2 is in line with the Sun and the Earth, but about 930,000 miles farther from the Sun than the Earth is, and about 4 times as far from the Earth as the Moon ever gets. The JSWT is never in shadow, so its temperature is stable, and its sun shield enables the optics and electronics to operate 50 degrees above absolute zero. There's no atmosphere in space, right? So there's no atmospheric turbulence, and thus no need for adaptive optics. But why send a near-infrared spectrograph into space? There are 2 reasons. First, the expansion of the universe means that the ultraviolet and visible light emitted by the earliest stars and galaxies has become infrared light by the time it reaches us. This phenomenon is called cosmological redshift. Second, the Earth's atmosphere blocks most infrared light from reaching ground-based telescopes. Let's be a little more precise about redshift. The redshift Z of a photon is its current wavelength, lambda, divided by its wavelength, lambda naught, when emitted, -1. The 1 is there to make the redshift of light 0 when it's emitted. At redshift 1, here and now, hydrogen's prominent Lyman alpha light has a wavelength of 0.1216 microns, which is in the ultraviolet range. But if you look just at redshift 1, lambda over lambda naught is 2. 2 minus 1 is 1. So the wavelength of light emitted, say 7.94 billion years ago, is now double what it was when emitted. Any emitted Lyman alpha that we receive today is still in the UV at 0.2432 if it started out 794 billion years ago. For some of the first stars at redshift 20, lambda over lambda naught is 21. So the wavelength of light the wavelength of light received is 21 times what it was when emitted. And the Lyman alpha that we receive today is in the IR range at 2.55 microns. 1 micron is about the limit of visible light. Okay, so this is why we need a spectrograph in space. I'm going to skip this about the cosmic microwave background because it has redshift 1089, and Lyman alpha was not emitted much in those years. But you can see here the infrared astronomy is needed because what we have in the beginning, the blue light curve, is not what we receive today. The first stars in the universe, so-called population 3, formed when the universe was about 100 to 200 million years old, which corresponds to redshift Z between 20 and 30. These early stars are much more massive than the sun, tens to hundreds of solar masses, and maybe a lot more. They emitted mostly ultraviolet light and have never been observed and confirmed. Their ultraviolet light's been traveling for well over 13 billion years through space that's been expanding. All photons lose energy, become longer wavelength as the universe expands. And that's what we mean by the red shift. In the diagram, the first star's light has been redshifted from ultraviolet light to near infrared light, and or even mid-infrared light. The James Webb Space Telescope is designed to observe the universe in the orange, red, and near-infrared wavelengths. So we'll get a good bit of light from those early stars. The kind of research that NIRSpec supports is voluminous. First, finding and studying the first stars and galaxies. Second, investigating the period of reionization when light from the first stars began to ionize the neutral hydrogen that filled the universe. Third, determining whether black holes formed even before the first stars, so-called primordial black holes. Fourth, figuring out how galaxies were first assembled. Fifth, learning about the birth of stars and protoplanetary systems. Sixth, studying the birth of planetary systems. And seventh, understanding the origins of life. And here are the specifications of NIRSpec. NIRSpec is sensitive to visible from visible red to mid near infrared, 600 nanometers to 5,300 nanometers. Its field of view is 3 arc minutes square, and it can operate at low resolution, R equal 100 with a prism, medium resolution, R equal 1,000 with a couple of gratings, and high resolution, R equals 2,700 with other gratings. The red part of the diagram shows the path that light takes through this NIRSpec. The thing to see here is that it has to be folded many times to fit into a small space. You think that with all that space out there, space wouldn't be so cramped. Okay, so NIRSpec has selects objects in 3 ways by using the micro shutter assembly. Okay, its long slit spectrograph selects a sliver of the exposed light to send to a disperser, a prism, or a grating. 5 slits are available. Its multi-object spectrographic mode uses the micro shutter mechanism, an array of tiny shutters used to select portions of the focused light in a much more flexible way. And NIRSpec has an integral field spectrograph which slices all of the focused light into slivers. In each of the three modes, each sliver produced is dispersed into a spectrum. Its configuration is very flexible. There are three sets of choices to make: filters, selectors, and dispersers. The filter wheel assembly has 8 positions, and 4 of which are for science. The micro shutter assembly contains 3 types of selectors: a multi-object selector for 250,000 tiny shutters, computer controlled, that allow 100 spectra to be recorded at one time. Second, the micro shutter assembly has 5 fixed slits that it can be used to pick. And third, it has the integral field unit aperture that can be selected. And then finally, we have the grating wheel assembly that contains a prism, 6 gratings for dispersing light, plus a mirror for target acquisition. Here's how the micro shutter process works. I think this slide and 3 more to go. NIRSpec's micro shutter mechanism is the most innovative selector mechanism. Here's how it works. The telescope's optics bring light to a focus on its focal plane, where the shutter array is, and then a computer opens some of the 250,000 shutters. And then each portion of light allowed through by the shutters is ultimately dispersed into spectra that fall on a detector array. And the results, there's some interesting results here due to James Webb. You've seen the fantastic pictures that have come from that Space Telescope's camera, but these results are due mainly to the spectrographs. So in looking for the first stars and galaxies, one goal was to find stars from Z equals 20 to 30. And the furthest one found so far has redshift of 14 and a little more. The other thing we would talk about was primordial black holes. In the little red dot, Cannock's LRD Z86 is at Z8.6. And there's an active nucleus with a 100 solar mass black hole. The black hole may have formed before the galaxy had a lot of stars. So it may be formed by direct collapse of a large amount of material rather than by the collapse of large stars. There's another thought that maybe it's a giant star, like millions of solar masses, and that it could have happened only in the early universe. So in galaxy GHZ2, redshift 12.34, NIRSpec found the most distant black hole ever located, and it was formed less than 400 million years after the Big Bang, and may also have formed rapidly. So in summary, we've answered questions like, what are spectra? What do astronomers learn from spectra? How do astronomers produce spectra? What are some important spectrographs? What are some recent results obtained by using these spectrographs? Finally, I should make some acknowledgments. First, to Isaac Newton and his many successors in using light to study the universe. Second, to my wife, Nancy, for helping me rehearse the talk. To Mary Duca for letting me use my MacBook. To John Sitchell and Rob Rezvani for helping integrate my Mac into Sperry's presentation setup. And finally, to use my curious and attentive audience. Thanks for your attention.